Essentials of the Tensor Calculus. This is the first of a 5-part series of webinars that take a look at the essential ingredients of the Tensor Calculus. Here's my involvement. In my 1970 PhD thesis on relativistic cosmology, I had to take a look at things like continuous groups, differential geometry, tensor calculus. Then, while preparing the manuscript for my 2001 Advanced Engineering Math book, I formulated and taught a course on tensor calculus, intending to include that material as a unit in the text. Alas, the manuscript was already too long for the publisher, and that material never made it into the book. All of the text that I've ever looked at on the tensor calculus are just loaded with notation and essentially abstraction, because there's not a whole lot of insight and understanding. The formalism is what's there, but the insight as to what this stuff means is not there. And a typical example, the definition of a tensor is given as an object that obeys a particular transformation law. But what is the object? What does the object look like? You get very little insight into what that would be. So the Rose-Hulman course that I prepared and taught looked at the essentials. I wanted to make the subject transparent to the undergraduate students that I was teaching. Then over the years, I've updated these materials using newer versions of Maple, and in this webinar, I've again refined and distilled these materials, and I'm using the newest version of Maple. Now, much of the formalism of the tensor calculus builds on ideas from multivariate calculus. So there are 3 themes, and these are divided into 5 parts. Now, the first theme are the preliminaries from multivariate calculus. The first part will take us down through these 4 topics: coordinates, coordinate change, Jacobian matrices, how they related, natural basis vectors of either tangents or gradients. Second part, we'll look at the relationship between tangent and gradient basis vectors, they're called reciprocal vectors. And then we look at what happens when you change coordinates for these tangent and gradient basis vectors. So that's the first third, and that's been split into these 2 parts. The second third is the tensor algebra, or the manipulations on tensors themselves. And so there I will address what is a tensor. Then you have this thing called a metric tensor, and what is this business about raising and lowering indices. So that would be the third webinar. The fourth and fifth cover what happens to a tensor under an infinitesimal change. That's what calculus is all about. And so that gets you into Christoffel symbols, and so there's enough material there in Christoffel symbols to constitute one webinar. And then once you've got Christoffel symbols, you can talk about covariant derivative, which is differentiation of this tensor object, and that will be the final webinar. So today we're going to begin with the notion of coordinates and coordinate changes. So let's begin with these preliminaries. First of all, it requires notation for coordinates. And here is the notation that we will use. Bold X or bold U represents a collection of coordinate names. Coordinate names are in script characters, and they carry a superscript, generally a numeric superscript. So 1 through n, 1 through n. Typically, I would use here x as a present coordinate system. U would be a new coordinate system, one that I'm changing from x to. So we've let the cat out of the bag here. We want to talk about what happens when coordinates are changed. And so we'll use this tableau to clarify our thinking. And you might want to think in terms of something familiar like polar coordinates as we lay the groundwork for a general discussion. Okay, so when you think of polar coordinates, you might think of either this form of the equations or this form. X, y. So here I'm using x and y rather than an x1 and an x2. Well, they would be the present coordinates. So the new coordinates would be r and theta. So instead of here using u1 and u2, I keep the familiar r and theta. And so when you think about how you would use these formulas, you would need to know an r and a theta. So you know a u. You know a new coordinate. And you want to bring that back to the present coordinates. And so that mapping is called an inverse. I use phi. Phi inverse is the return map. It's the mapping that brings you back from the new coordinates u to the present coordinates x. If you write polar coordinates in the form r equals root of x squared plus y squared, theta is arctan y over x, then you know an x and a y, so you know a present coordinate, and you are sending it to the new coordinates. Here are theta, in general u1, u2, and so the function phi expresses how to get from where you are now to the new system. So that is the forward map, and this is the inverse map, and that will be very important throughout all of this discussion. Now, each of these transformations, whether it's forward or backwards, has a Jacobian matrix, and this is my notation for the Jacobian matrix. It will be AJ, bold, Roman, with a subscript. So if you take the Jacobian matrix of these equations, it will be expressed J sub phi, and it will be a matrix of derivatives. And this is the notation that you will see used. dui, I is in superscript, dxj. Because look, you have x's here. These are the independent variables, x and y, or x1 through xn. Those are the independent variables. That's what you can differentiate with respect to. These functions, here r and theta in general, u of the x, right? U of the x in general, those are the dependent variables. So this is a representation of the Jacobian matrix, and we'll see this many more times, and it would look like this in r, theta, x, and y notation. So u1 differentiated with respect to x1. u1, in other words, the upper script here in the numerator is a row index. The derivatives, x, y, that's j, that's a column index. So think of this as a row column. In the first column where x stays 1, you'll notice that you differentiate with respect to x the two u's, or theta. That same pattern exists here too. If you differentiate xy with respect to r theta, then you get dxi duj. In the first column, the derivative remains the same. It's with respect to u1, but u1 here is r. So the two derivatives in the first column are both derivatives with respect to r. In the second column, the derivative is with respect to theta. In the first row, it is the x function, the first function, that's being differentiated. In the second row, then I becomes 2, then it is the second variable that gets differentiated. That's the pattern. Most people have come through a calculus sequence, have seen this stuff, but those are the essential ingredients that you have to pull to the surface as you think about tensor calculus. Now, an essential fact is that these two Jacobian matrices are inverse as matrices, and that's what we want to explore next. But it takes a few steps to do that. First of all, there are two identities that we need to begin with. If you write x is a function of u, okay, so that function can be called phi inverse because you are pulling back from the new system to the present system. Now, u itself can be expressed in terms of x. It is indeed phi of x. So phi inverse of phi of x returns x, and this is an identity. And you can do that same identity or same kind of identity going the other way. U is a function of x. That's u is a function of x. So you think this way if you're thinking polar coordinates to make it concrete. The x is a function of u. It's phi inverse of u. So phi of phi inverse is u. So that's where we start as we do a calculation that verifies that these two matrices are inverse matrices. Now again, to make sure that everything is concrete and not just a bunch of symbols thrown around on paper, let's do that kind of calculation for polar coordinates. Here's x. That's this x right here. It's the vector in our notation with two coordinate names, x and y. The function of r and theta are listed here. Now, if this r is replaced by the root of x squared plus y squared, and theta is replaced by arctangent y over x, then you are computing cosine of the arctangent, sine of the arctangent. If you draw a little right triangle and figure out what cosine of the arctangent and sine of the arctangent would be, they turn out to be x over the square root of x squared plus y squared and y over the square root of x squared plus y squared. These square roots cancel. You get back x and y. That's the vector x. This is the kind of calculation that you have to go through once in your life to understand what these basic identities look like. And if you go the other way, you start with u. U has two coordinates, r and theta. What is r? What is theta? Here, square root of x squared plus y squared, arctan y over x. If you put in for x, r cos theta. If you put in for y, r sine theta. Clearly, this is going to simplify to r. You can see that you factor out the r. You got an r squared, you bring it out, it comes out as r. Cos squared plus sine squared is 1. And here you are taking the arctangent, y over x. The r's cancel, you get sine over cosine. It's arctan of the tan. It's theta. r theta, that's the vector u. So you have clearly seen this before, probably have done something like this once in your life, but that is the idea behind these two basic identities from which we will build a proof of the that the Jacobian matrices of the two transformations phi and phi inverse are matrix inverses. Now we would to get to Jacobian matrices, you have derivatives in the Jacobian matrix. These derivatives are going to be taken by the chain rule. Now here I'm going to do a calculation, and I'm not going to muck it up with superscripts, so I'll use just plain regular simple notation. We have two sides to consider. So suppose we look at u is phi of x of u. So you're looking at an identity of the form u is u of x and y, but x and y are themselves function of u and v. And that's why this is an identity. And you differentiate that identity with respect to u and v. Well, when you differentiate this identity, you will get a 1 here. And when you differentiate this identity with respect to v, you'll get a 0 here. And so there's your 1 and there's your 0. Now apply the chain rule. du, dx, dx, du. You see that? du, dx, dx, du. Plus du, dy, dy, du. du, dy, dy, du. Down here you're going to get du dx, dx dv, du dy, dy, dv. Okay, then you're at the other companion identity for the other coordinate. V is a function of x and y, who are in turn functions of u and v. If you differentiate with respect to u, then you're differentiating v, you will get a 0. If you differentiate with respect to v, on v, you will get a 1. And the derivatives by the chain rule are dv, dx, right? dv, dx, dx, du. dv, dy, dy, du. dv, dy, dy, du. And down here, it will be dv, dx, dx, dv, dv, dy, dy, dv. So at one time in a life, a mathematical life, it behooves each of us to go through these calculations to make sure that they're in the brain somewhere, so that they don't appear as mysterious when they are called on for various purposes. And here you're going the other way. You have x as a function of u, which u in turn is a function of x. So x is a function of u and v, but u and v in turn are functions of x and y. And you differentiate first with respect to x. This x differentiated, you get a 1. When you differentiate that with respect to y, you get a 0. dx, du, du, dx. dx, du, du, dx. dx, dv, dv, dx. dx, dv, dv, dx. Down here, it's dx, du, du, dy. dx, dv, dv, dy. And down here, you differentiate the y statement with respect to x, you get the 0. And when you differentiate the y statement with respect to y, you get the 1. And then it's chain rule dy, du, du, dx, right? dy, du, du, dx. dy, dv, dv, dx. And here it's dy, du, du, dy. dy, dv, dv, dy. Okay? These four equations here, fundamental, basic, important. These four equations here, basic, fundamental, important. They will be the basis on which we can conclude that these derivatives, which appear in the Jacobian matrices, make the Jacobian matrices inverse matrices. Now this is really next just a little aside where I want to show that these very calculations that we have just looked at can be reproduced in Maple. So here are some notational devices that make the outcome look presentable. Here are the basic identities. X is a function of u and v, which are in turn functions of x and y. Y is a function of u and v. U and v in turn functions of x and y. And here, u is a function of x, which is x and y, which are in turn functions of u and v, and so forth. If you apply differentiation to this identity, you get the anticipated result. 1 equals and partial derivatives. If you differentiate that identity with respect to y, you get 0 here, and here is the y identity. You differentiate with respect to x, you get 0. You differentiate with respect to y, you get 1, and the derivatives here are the same derivatives that we wrote by hand in this tableau. Here, just check one of them. du dx dx du. Sorry. dx du du dx. This is what happens. It becomes a blur, and this is what will happen if this stuff is not clear in your head and you're paying attention to what you're doing. dx du du dx. Notice you get the dx du du dx plus here it's the x dv dv dx, and up here it's the x dv dv dx, and you can check that out on all 8 of these, that yes, you can reproduce those derivatives in Maple and make it look just like you would make it look with a pencil and paper. And this is what it would begin looking like when you pick up a textbook on Tensor Calculus. You're going to see these same expressions done where the variables are superscripted. And if you step back for a second and you look at this mass of symbols, you can become exceedingly daunted by all of this. And that's why I showed what it looks like in a simple case that you're familiar with, polar coordinates, so that when you look at this description of what we just did, you can say, oh yeah, I understand that because I saw it for polar coordinates. So here are the 2 dependent variables, or dependent variable function names, x1, x2. They are functions of u1 and u2, but u1 and u2 are in turn functions of x1 and x2, so you have these basic identities. And on this side, you have the phi mapping. U is a function of x, which is in turn a function of u. And when you apply the chain rule, you're going to be using the superscripted variables. The x1, dx1. You get 1. And you apply the chain rule. dx1, du1. du1, dx1. And then you have du1, du2, du2, dx1. Now notice what happens here. 1 here, 1 here, 2 here, 2 here. And that's why it can be written with a sum, where this one and that one are summed on. And so you have a k sitting here and here, and you sum on the k. And 1 up here, 1 down here, 1 up here, 1 down here. Second equation, where you have 0, you're going to have 1 here, 1 here, 2 here, 2 here, 1 here, 2 here, 1 here, 2 here. So 1 here, 2 here, and k that you sum on. Same thing happens down here. 2, 1, 2, 1, 1, 1, 2, 2. So you sum on this index, 2, 1 here. And finally down here it's 1, 1, 2, 2. So you sum on that pair of indices. and it's 2 here, 2 here, 2 here, 2 here, 2, 2. So these are the sums that show up in a formal treatment, and until you pull them apart and say, what do these things really look like? What do they say? It can become very, very confusing. On this side, you have the exact same structure. You've just changed the letters. You've interchanged X and U. That's all you've done here. Okay? Wherever you see an X on this side, you're going to see a U on this side. And wherever you see a U on this side, you're going to see an X on this side. And you're going to get the same pattern, 1, 1, sum this way. 1, 2, 2, 1, 2, 2. Okay, so we have the machinery in place that will allow us to multiply Jacobian matrices. And I'm going to do the same thing I did a minute ago. First, I'm going to do it with a more traditional notation using no superscripts. And I want to look at the product of this Jacobian matrix for the inverse transformation times Jacobian matrix for the forward transformation. And here is the product in the reverse order. So what does this Jacobian matrix look like? Remember, this is X as a function of U. So you can differentiate with respect to U. So in this column, the derivatives are with respect to U, and in this column, the derivatives are with respect to V, and you differentiate the functions xy, xy. Now, this Jacobian has had its rows grouped, and we'll explain that eventually, why we did that, but just go down the column. The derivative with respect to x appears in this column, and the derivative with respect to y appears in this column. Now, when you do the matrix product, you're going to get the x du, that's this term, times du dx, that's this term, plus the x dv, that's this term, times dv dx, that's this term. Right? And you can begin seeing what's happening here. This sum, remember, u this way, v this way, 1, 1, 1, 1, okay? This sum we have already seen from the basic identities is 1. And here, uu, vv, xy, xy, those are different. That's the 1, 2, and that's 0. And here you have the same thing happening, uu, vv, but yx, yx, that's going to give you 0. And over here it's yy, yy, uu, vv, and that comes out to be 1. And that's the reason for looking at those basic identities, because that's where these sums are worked out to be 1s and 0s. And so this product is the identity matrix. And you do exactly the same thing here. Again, the Jacobian matrix for the forward transformation has its rows grouped, because we'll talk about the reason for doing that eventually. But it's a Jacobian matrix. This first column has its two functions, u and v, differentiated with respect to the one variable x. This column, the derivative is with respect to y. And this Jacobian matrix we examined over here, and you take the product du dx, that's this term, times the x du, that's this term, plus du dy, that's this term, times dy du, that's this term. Xx this way, yy this way, uu, that sum is 1. And similarly, uv, that sum will come out to be 0. Vu, that sum comes out to be 0. V, 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 that sum comes out to be 1. And so this is how you establish that the product of Jacobian matrices for the forward and backward transformation are inverse matrices. And really, once you convince yourself of that in n equals 2 case, you walk around with that in your head and you say, well, yeah, it's true. I accept it. You can go ... to n and generalize, but until you see it in a simple case and you convince yourself this is what this stuff means, it's a mystery. Now, what you will see in the typical textbook will be something that looks more like this. Product of the Jacobi matrices, and superscripts will be used on the variable names, but we have just gone through it in terms of x and y. We understand what this stuff means. Okay? These sums will be expressed as sums, and maybe even without the summation sign, because of this blanket Einstein summation convention, which says sum on a repeated index. Okay, so at this stage, the summation sign may already be dropped in the presentation, but this is what it looks like in terms of superscripted variables, and it can be daunting unless you really know where this stuff came from. Right? 1, 1, sum on the k, that case we know comes out to be 1. 1, 2, and 2, 1 we know come out to be 0, and 2, 2 we know comes out to be 1, and you get the same thing happening here. This is just a tight way to say Jacobi matrix. Jacobi matrix. This is our expanded view. I group the rows of the Jacobi matrix of the forward transformation. Explanation yet to come, but the columns have the same derivative with respect to x1, and in this column with respect to x2. This is the Jacobian matrix of the inverse transformation, phi inverse, and you get these sums which we have just seen generated by the chain rule. You can express those sums with more compact notation. 1, 1, that we've discovered comes out to be a 1. That sum comes out to be 1. 1, 2, and 2, 1, 0. And 2, 2 comes out to be 1. So this is what it looks like in a typical textbook, if they take the trouble to go through this much detail. The general case looks even worse, because this is what the general case looks like. You have 1 to n, a lot of dots, a lot of symbols, and out of this you are to construct the thought, the conviction, the confidence that the product of Jacobian matrices for forward and backward transformation in either order are inverse matrices. Delta ij is the Kronecker delta when the two indices on this symbol agree. So when it's 1, 1, 2, 2, 3, 3, you get a 1. So those are the diagonal elements. And when these two indices are different, you get 0. Those are the off-diagonal elements. So this is a representation of the identity matrix when you think in terms of multiplying matrices. If you jump in at this level and you're looking at this mass of symbols, well, I can only speak for myself, and I can only speak for the kind of students that I taught at Rose-Hulman. If you hit people with this up front, it's opaque. There's no understanding this stuff until you go back and say, well, where did this come from? What does this stuff mean? And that's why I organize this as I have, and I have made this statement down here. I don't think the general case is enlightening, because the way my mind works, to generalize, I look at case 1, case 2, case 3. When I become convinced, I say, oh yeah, case N. Oh yeah, it's the nth. I just can't approach this any other way. Now we're ready to talk about natural basis vectors. And the basis vectors come in two varieties. They can be tangent or they can be gradient. Let's look at tangent vectors. These are much more familiar. So you have a position vector r, and it generates coordinate curves. Just think of polar coordinates. Concentric circles, radial lines emanating from the origin, those are coordinate curves. And we want to talk about tangents to those coordinate curves. They form a basis at each point in the manifold. When we differentiate with respect to a coordinate variable and get a tangent vector, we will use a subscript to express the fact that this is a tangent vector. And what are we differentiating? Well, think in terms of x of u. So this is x equals r cos theta, and this is y equals r sine theta. And we're differentiating with respect to r first, and then we're going to differentiate with respect to theta second. So this is what these derivatives will look like. And so this vector is E1 and this vector is E2, and they're tangents to the coordinate curves. It turns out, if you're paying attention, that EK is the kth column of the Jacobian matrix for the inverse transformation. Right? This is dx, this is dy, and both with respect to r. That's a tangent vector to the coordinate curve, and is a column, the first column, of this Jacobian matrix. And this is the derivative with respect to theta, if you're thinking in terms of polar coordinates. And what we conclude from this discussion is basis vectors that are tangents to coordinate curves will carry a lower index. So now let's look at gradient basis vectors. Okay, a gradient on a coordinate surface. And what is the coordinate surface? Well, that's defined as u as a function of x. And gradients are orthogonal to these surfaces. Gradient is orthogonal to any surface for which you computed the gradient. And we will use a superscript on a gradient vector. So the natural basis gradient vectors would be this collection of vectors that we will designate with an upper script, superscript. Now let's look at that in case n equals 3, because that's where you think about surfaces. And so you have a function of 3 variables. Think of this as x, y, z. So you have a function of x, y, z. So you think in terms of spherical coordinates, rho of x, y, z, phi of x, y, z, theta of x, y, z, and you take gradients. Well, if you differentiate with respect to, or take the gradient of that first function, it will look like this. The function stays the same, so across the numerators it's u1, u2 here, u3 here, but the derivatives are with respect to each of the independent variables, x1, x2, x3, or xyz if you want. Okay, so these 3 vectors would be gradient vectors perpendicular to the coordinate surfaces. Now, if you're paying attention, you'll see that these coefficients or components of the gradient vector are the elements of the rows of the Jacobian matrix J phi, which is why we group those rows when we looked at products of Jacobian matrices, because those rows have a special meaning. So think about this Jacobian matrix. DUK dxj. This is the row index up here. This is the column index. So you pick a row, row 1. In row 1, the derivatives are with respect to x1, x2, x3, or xyz if that makes it more concrete. Okay, so the kth row of the Jacobian matrix, J phi, is one of these gradient basis vectors, and we use a superscript to express the fact that it is that kind of a vector. So I think this is a good stopping point. Having looked at notation, coordinates, Jacobian matrices, natural bases of tangent and gradient vectors. Now the material for part 1 will be available to anyone who contacts me by email. So my email address is rlopez@maplesoft.com. rlopez@maplesoft.com. And if you're going to continue participating in the remaining webinars of the series, it might be useful to obtain this material so you would have it to review before our next webinar.